So probably our last video of substitution reactions. I'm so depressed. I've had such a good time talking about cheating carbons and pretty nucleophile groups and saying sweet nothings in your friend's ear and trying to persuade them to cheat or not to cheat, and carbon rearranging its life together to try to figure out its best purpose in life. I mean, all of these life lessons wrapped up into organic synthesis questions. It's kind of depressing. And the semester's almost over. On top of that, we just have one more lecture left. So let's take a look at this last example problem that I want to do with substitution. And this question says, for each of the following pairs of SN2s, indicate the one that occurs with the greater rate. Okay, so which one's preferred? So let's look at A. A, I have a organic, 3 carbons in a row with chlorine, with OH. And then I have an organic, 3 carbons in a row with chlorine in the middle. And there's an OH. All right, so the first thing I want to say, good news for you. This is OH minus, and OH minus is a very strong nucleophile, and strong nucleophiles really love SN2s. I mean, these things are super sexy, super pretty. Hubba, hubba, hubba. So here we have a propyl group with a chlorine and a propyl group that's really an isopropyl with a chlorine on it. SN2s, keep in mind, cheat. Cheat, 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 cheat. So the less there are around the halogen, the better it is, or the carbon with the halogen, the better it's going to be for SN2. This chloro group is primary. This chloro group is secondary. Primary groups have a greater affinity toward SN2 because this OH group can get into that carbon and cheat through the back door while that carbon leaves out the front door. So this one is going to be the fastest for the SN2 reaction. Let's look at B. 3 carbon with a chlorine and an OH. 3 carbon with an iodine and an OH. All right, well, first off, OH minus, OH minus. I've brought my super pretty friends to the party. So that ensures SN2 will happen. Carbon is going to cheat. I mean, there's just no way around it. It's going to cheat. I try and try and try to tell him or her, just won't ever listen. That is not the way you're supposed to act. But sometimes that's just how carbon is. Overlook it. We also see no difference in the halogen type, the carbocation type. This chlorine is on a primary. This iodine is also on a primary. So they're pretty prime positions to be cheated on. I mean, that OH group can go through the back door with either one of these. The issue, though, here is that that's not really the difference that they want me to look at. What they want me to look at here is the chlorine and the iodine position. The uglier one is going to be kicked first. The uglier it is, the more willing you are to get rid of it. Okay? That's just how it is in this world. Again, it's sad, but there you go. No one said politically correct. All right, so out of these two, iodine is way ugly. Iodine is large and big and just disgusting. Disgusting looking. That's just the way that this carbon sees it. I'm sorry. That's the way carbon sees it. Not the way I see it. Don't blame me. Don't get mad at me. You blame that carbon right there. So this carbon's going to look at the iodine and it's going to go, off you go. I'm tired of you. You got to go. I don't want you anymore. I mean, that's just carbon's mentality. So because of that, this one is going to happen faster because iodine is a better leaving group. So propyl chloride reacting with hydroxide, or propyl iodide reacting with hydroxide. Propyl iodide is better at a nucleophilic substitution bimolecular reaction because iodine is more nucleophilic, or a better leaving group than the chlorine is. That's how we're going to regard that. Did you understand that terminology? Did you understand that description of what I just weaseled in? If you did, good job. You've been doing your job very good. Now let's take a look at C. We have 3-carbon chain with bromine and OH, and a 3-carbon chain with bromine and H2O. Which one's going to be better? Okay, so apparently they don't want me to compare the alkyl halides, do they? No, this is propyl bromide and the other one's propyl bromide. So there's no difference here. They just want me to ignore that because it's the same. What they want me to place a focus on is this OH group and this H2O. Here I have a pretty friend I brought to the party, and here I have just an okay friend that I brought to the party. SN2 is going to be a cheater. So which one of these would be more prone to cheating? And that would be my pretty friend. So if carbon's going to cheat, he's going to do it, or she's going to do it, with the prettiest ones that I bring to the party, and that is the OH group. So this setup is going to be better for an SN2 reaction, and the reason is because propyl bromide reacting with hydroxide is going to be a better setup than propyl bromide reacting with water, because hydroxide is a better, stronger nucleophile in order for the substitution reaction to take place. That is why we choose that one. It's got a negative, bottom line. D. 3-carbon, bromine in the middle, 3-carbon, bromine in the middle. Okay, so apparently they don't want me to do anything with it, whatever. They want me to focus on other things of the problem. So what they want me to focus on here is this CH3O, and then down below they've wrote water and methanol, and then here they wrote CH3O, and they've only wrote methanol there. So really the difference here is water. All right, so water in this case, let's think about what they want me to think about. I mean, water is the only difference between the two. So this is a solvent, really. And this solvent is a protic solvent. Oh, I see, right? That's what they want me to do. So protic solvents, think about reverse. It reverses things. So what was pretty is not really pretty anymore. Okay, so if I take a look at these two, which way would carbon be a cheater? So here the OCH3 is a pretty friend. I brought it to the party. That carbon looks at it and goes, The issue here, though, is that water is a protic solvent, and it surrounds that pretty friend. So even though I brought the pretty friend to the party, there's all of these other people that are surrounding that person, and this carbon never has a chance to get in and make a move. That's like a Debbie Downer moment, right? But that's the role that a protic solvent plays. Out of this scenario to the right-hand side, I brought my pretty friend, and I know there's methanol here, and I know that methanol is slightly protic as well, but folks, this is protic and protic both. I mean, they brought extra protic here. There's extra friends at that party that's taking up this methoxide's time. So out of these two options, this one is actually going to react quicker because this carbon has more of a chance of going in and cheating with that methoxide. This one, not so much. There's just too many people there. There's too many people surrounding that methoxide. This carbon can't get in to make a move in order to cheat with in the first place. So out of the two possibilities, my 2-bromopropane reacting with methoxide and some methanol will be a better choice than 2-bromopropane with methoxide and some methanol and water. And it's simply due because water is a protic solvent that takes up the methoxide availability. Now for E. Last one. Short video, maybe. All right, so here we see bromine with a CH2, 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 NHCH3. And then we see a bromine with a CH2, 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 NHCH3. All right, so it looks like the only difference here is maybe the addition of a carbon, right? So you're scratching your head and you're saying, well, they didn't bring a nucleophile in. No, they didn't. Not like they did up above. OH minus, OH minus, OH minus, OCH3 minus. They didn't really bring in an extra nucleophile. And that's okay with this one. Why is that okay? I don't understand. Well, okay, this goes back to the intermolecular and intramolecular reactions. And remember, I said in one version, you could just be a molecule on your own and decide that you have a much better time by yourself than with another person. Okay, well, this is one of those examples. These molecules are going to have a good time on their own. Which one would happen, though, a little bit faster? And I told you you'd probably never see these types of questions on a test. You might see something in Blackboard or something very simple. But here you need to understand that this is going to ring around. I mean, this carbon and the bromine is a very good leaving group. So this is slightly positive. This nitrogen has some free sets of electrons on it that's negative. So there is an attraction here that goes on between the nitrogen and that carbon that has the leaving group on it. So the answer to this question is which one could form the ring structure and have it be a little bit more stable. And the one to the left is going to do that faster. So it reacts faster in an SN2. And the reason is because there's an extra carbon in here. So when it does make this ring structure, this is a bigger ring that doesn't cause as much strain on the ring to break apart. So 1, 2, 3, 4, and that nitrogen is going to be the fifth one that's in that ring system. That is a much better setup than if you only had a nitrogen with 3 carbons that come around, right? I mean, here's carbon 1, there's carbon 2, there's carbon 3. That's what you would get in this scenario over here to the right-hand side. So this is more restrictive. It pulls the ring in tighter. It's going to pop open a little bit because those angles are not ideal. So if we add in an extra carbon, it goes to a 5-membered ring, which is what we get over here, 4 carbons and a nitrogen. And that allows the ring a little bit more stability because the bond angles are not pulled as tight. Now, again, you might see something similar on an online assignment, but you're probably not going to see these types of questions on a test that I will give you. I just think there's an appropriate time to talk about these types of reactions, and it's not right here. All right, they're going to introduce them. They're going to throw them out. You might see them here and there, but it's not something that I'm going to majorly focus on throughout this lecture module, throughout this chapter, and it can be much later on in a different organic class that will talk about them. All right, so this is the summary of substitution. So 2 types of substitutions, SN2 and SN1. Secondaries, benzylics and allylics, do both. If you go back and take a look at primaries, primaries love to cheat, and tertiaries cannot cheat. Too many neighbors around them. As far as SN1 goes, carbons being single for a little bit, tertiaries love them. They got friends. Primaries, not so much. They need that support system. SN2, another thing, this always inverts. They have to sneak through the back door. SN1, you get a mix. If stereochemistry is involved, you will get a mix of the R's and the S's that go forward. And finally, out of the 2 systems, the SN2s prefer the negatives, and the SN1s prefer the ones that have no negatives, that have a hydrogen that can easily be removed throughout this process. If you keep this in mind, jot this down, use it as a reference. When you read these problems, you don't really know which one's going to happen. I think this will kind of send you in the proper direction of a proper substitution reaction. Whether or not a 2 version or a 1 version will go forward. And then keep in mind, SN2, no rearrangement, and SN1 allows rearrangement if it needs to take place. Sometimes it doesn't, but sometimes it will. Okay, so good luck in the substitutions. I mean, that's where this lecture module is going to end. I think we've done enough examples. It's just really finding the halogen, replacing it with a nucleophile, and then figuring out which mechanism goes forward, the 2 version or the 1 version. That's really all that we're doing in this lecture module, folks, okay? So if you've got questions, as usual, you know how to get in contact with me. You know how to get a hold of me. Send me those questions that you have. Good luck on the online assignments. And that's it of substitution. So we have one more lecture module left, and that's going to be on elimination. So keep in mind, substitution routes, elimination routes. We talked about the differences very early on in this lecture series, but we only focus on substitution for this. And in the next lecture, we're only going to be focused on elimination. What's the difference? You'll find out when that time comes.